Algebraic Structures, Lecture 21, Algebraic Closure. We start with the definition of an algebraically closed field. Definition: a field K is called algebraically closed, provided that any non-scalar polynomial with coefficients in K has a root in K. For example, the field C of complex numbers is algebraically closed by the fundamental theorem of algebra. A negative example: the field R of all real numbers is not algebraically closed because the polynomial x squared plus 1 with real coefficients does not have any real roots. An alternative description of an algebraically closed field is the following. A field K is algebraically closed if and only if, for any algebraic extension of this field, so K is a subfield of F and this extension is algebraic, we must have that K is equal to F. So a field is algebraically closed if and only if it doesn't have any non-trivial algebraic extensions. Indeed, if we have such an algebraic extension and A is an element of the bigger field F, then the minimal polynomial of this element over the field K must be irreducible, as we know, and hence it should have degree 1 since K is algebraically closed. And this means that A should be an element of K. Yet another description of an algebraically closed field is that a field K is algebraically closed if and only if all irreducible elements in the ring of all polynomials with coefficients in K, this should be K, not R, have degree 1. Now let us define what an algebraic closure of a field is. So let K be a field. Definition: an algebraic closure of K is a field extension K inside F with the following properties. First of all, this extension is algebraic, and the second property is that the bigger field F is algebraically closed. So for example, the complex numbers is an algebraic closure of the real numbers. A negative example: the complex numbers is not an algebraic closure of the rational numbers because the extension of rational numbers inside complex numbers is not algebraic. We know that there are transcendental elements even already in the field of real numbers. A trivial example: for any algebraically closed field K, the field K itself is an algebraic closure of K. Now we can formulate the main result of today's lecture. Theorem: any field admits an algebraic closure. Moreover, this closure is unique up to an isomorphism that fixes all elements of the original field. Notation: so the algebraic closure of the field K is denoted by K overlined. And intuitively we can think of K overlined as the collection of all algebraic elements over K. So the problem is that we should take all these algebraic elements over K and collect them together in one field. And this is not very easy. So note that Galois theory of finite algebraic extensions says that finite algebraic extensions usually have rather big automorphism groups. So when we collect all algebraic elements in one field, we should remember that there are many automorphisms of these things, and this makes the construction complicated. So that's our problem in constructing the algebraic closure of K. One of the main ingredients which we will need in the proof of the existence of algebraic closure is Zorn's lemma. So let's recall this set-theoretic axiom. So Zorn's lemma: let M be a partially ordered set. Assume that for any totally ordered subset N of M, there is an element Q in M which is greater than or equal to than all elements in our totally ordered subset. Then M contains a maximal element, that is an element M, such that for any element A in M, From the inequality that m is less than or equal to a, we must get that m is equal to a. So this is called Zorn's lemma, but it is equivalent to one of the axioms of set theory, and that's the axiom of choice. So we can treat Zorn's lemma as an axiom. Basically, the axiom of choice says that the Cartesian product of any collection of non-empty sets is non-empty. And the third famous result to which the axiom of choice is equivalent is the well-ordering theorem. And the well-ordering theorem says that every set can be totally ordered such that every non-empty subset has the minimum element. So Zorn's lemma, axiom of choice, and well-ordering theorems, these are equivalent statements in set theory, and we treat them as axioms. So now let's move to proving the existence of algebraic closure. So let K be a field of cardinality kappa. Let M be the set of all monic irreducible polynomials in K. For each of these polynomials, let us list all roots of this polynomial. So each polynomial has finitely many roots, so let's list all of them without repetitions. And let us denote by capital K the union of all these algebraic elements over K. So the capital K is the list of all algebraic elements over the small k without repetition. It is very easy to see that the cardinality of K is countable if little k is finite, and otherwise the cardinality of capital K is the same as the cardinality of the little k, that's kappa. This is because we have countably many degrees for polynomials over K, and therefore the cardinality of the roots, each polynomial has finitely many roots. If we take all them together, we will get exactly the same number of elements as in the original field, if this field is infinite. Consequently, the cardinality of the set of all algebraic elements over our field small k is bounded from the above by the maximum between Aleph 0 and kappa. So let us fix some cardinal nu, which is strictly greater than both kappa and Aleph 0, so we can make a uniform proof both for finite and infinite fields. And let S be a set of cardinality nu, which contains our set K, so our field. This is of course possible because we assume that nu has cardinality greater than the cardinality of K. Now consider the set F of all algebraic extensions from K to capital F, for which the underlying set of the field capital F, so for the bigger field, belongs to S. Note that up to isomorphism, each algebraic extension of K belongs to this list F of algebraic extensions because the cardinality of the set of algebraic elements is strictly smaller than the cardinality of our set S. Also, our set F is partially ordered with respect to inclusions. And for any non-empty totally ordered collection of elements of F, the union of all elements in this collection clearly belongs to F. Therefore, by Zorn's lemma, our set F contains a maximal element. Let's call it the field L. And we claim that this field L is an algebraic closure of K. So we see we used Zorn's lemma to deduce existence of this field. So now let's argue that L is an algebraic closure of K. By construction, L is an algebraic extension of K, because anything in F is an algebraic extension of K. So we only need to prove maximality. So in particular, since L is an algebraic extension of K, the cardinality of L is at most the cardinality of the capital K, and this is strictly smaller than the cardinality of S. Assume that f of x is a polynomial with coefficients in L, which is irreducible. Let L' be the algebraic extension of L to which we add the root of this f of x. Then either L' is finite or its cardinality is the same as the cardinality of L. Since S is very big, so the cardinality of S minus L is equal to the cardinality of S, which is strictly bigger to the cardinality of L, then there is an injection from L' minus L into S minus L. And using this injection, we may assume that actually L' belongs to S. So we can realize our extension L' inside our set S. And this extension is algebraic because algebraic extensions behave transitively. A composition of two algebraic extensions is algebraic. And now we can use that we have assumed that L is a maximal element to deduce that L must be equal to L' because L is a maximal element in F. And this means exactly that L is algebraically closed because it doesn't have any algebraic extensions. And this completes the proof of the existence. Now we can argue about uniqueness of algebraic closure. So let K be a field, and let K inside capital K and K inside capital F be two algebraic closures of K. We have our theorem about extension of homomorphisms between fields. If we use this theorem, there is an extension of F inside L, and the homomorphism phi from capital K to this bigger field L, such that the following diagram commutes. So our little k is inside capital K and is inside F, and we can extend F to L, such that the homomorphism, the embedding of little k to F, extends to a homomorphism from capital K to L. We call this homomorphism phi. Next, any element in the capital K is algebraic over K, and so the image of phi must belong to F. And each irreducible polynomial over little k has finitely many roots. And so our phi, when we restrict it to the roots of this polynomial, it should of course send them to the roots of the same polynomial, but now in F. And they are finitely many, so it induces a bijection between these roots when we look at them as elements in capital K or as elements in capital F. Therefore, phi is in fact an isomorphism between capital K and capital F. So two algebraic closures of K are isomorphic. And this completes the proof of the main theorem. Now let us discuss the cardinality of the algebraic closure. Corollary: if K is finite, then its algebraic closure is countable. If K is infinite, then the cardinality of the algebraic closure is equal to the cardinality of K. Proof: if K is finite, then the ring of all polynomials with coefficients in K has countably many elements. Each of these elements has finitely many roots, and this means that there are countably many algebraic elements over K. This gives us the first part. If K is infinite, then K of x has as many elements as K, and each of them has finitely many roots. So if we put them all together, we get exactly as many elements as the cardinality of K. And this proves our corollary. Now let us discuss the terminology algebraic closure. So the meaning of the word closure. Observation 1. If K is algebraically closed, then the algebraic closure of K is equal to K. Proof: for an algebraically closed K, the extension of K inside K is by definition an algebraic closure, and we know that it is unique. That's it. Proposition 2. If K is a subfield of F, then the algebraic closure of K is a subfield of the algebraic closure of F. Proof: any algebraic element over K is also algebraic over F. And so any element in K overlined must belong to F overlined. That's it. And proposition 3. K is a subfield of its algebraic closure. Indeed, every element of K is algebraic over K, and this implies the statement. And these three observations together mean exactly that taking the algebraic closure is a closure operator. Okay, now let us talk about algebraically independent sets. Let K inside F be a field extension. Definition: a subset Q of the bigger field F is called algebraically independent over the small field K, provided that for any non-empty finite subset Q1, Q2, and so on Qk of this Q, and any non-zero polynomial over K in K variables, so f of x1, x2, and so on xk, coefficients in our field K, and the variables are x1, x2, and so on xk. So if we insert instead of these variables our elements q1, q2, and so on qk, we should get something non-zero. So the evaluation of any polynomial in any finite set of our variables should be non-zero. For example, one element is algebraically independent if and only if it is transcendental. So the notion of transcendental element is exactly the notion of algebraic independence for one element. If we consider the field of rational functions in two variables, then these variables form an algebraically independent set over the original field. So the variables of rational functions are algebraically independent over the original field. Now we can discuss the notion of the transcendence degree. Let K inside F be a field extension. Definition: the transcendence degree of F over K is the cardinality for a maximal with respect to inclusions subset of F that is algebraically independent over K. For example, the transcendence degree of F over K is 0 if and only if the extension K inside F is algebraic. Another remark: if Q is a maximal with respect to inclusions subset of F that is algebraically independent over K, then every element of F is algebraic over the purely transcendental extension of K inside the field of rational functions in the elements of our set Q. Now there is a statement which is called Steinitz exchange lemma, which we are not going to discuss, which implies that if we have two different maximal with respect to inclusions subsets of the bigger field that are algebraically independent over the smaller field, then these two sets must have the same cardinality. And this means that the transcendence degree of F over K is well defined. It doesn't depend on the choice of our maximal algebraically independent set. Now we come closer to formulation of a very interesting structural theorem about field extensions, which is called Steinitz theorem. So for every field extension K inside F, there is an intermediate field, capital K, greater than little k, smaller than capital F, such that the extension of little k inside capital K is purely transcendental. So this means that the only elements of this extension that are algebraic over the smaller field are the elements of the smaller field. And the second extension of capital K inside capital F is algebraic. In particular, every algebraically closed field is the algebraic closure of some purely transcendental field extension. This implies the following. So, theorem due to Steinitz: two algebraically closed fields of the same characteristic are isomorphic if and only if they have the same transcendence degree over the prime subfield. So this theorem was proved in the very influential paper by Steinitz, which is called Algebraische Theorie der Körper, and which appeared in Krell's journal in 1910. This has the following consequences. Corollary: for each uncountable cardinal and each characteristic, there is a unique aptoisomorphism, algebraically closed field of that cardinality and that characteristic. This corollary leads to the following interesting example. Consider the field C of complex numbers, and let us extend it to the field of rational functions in one variable x. And let's then consider the algebraic closure of this field of rational functions. Of course, the cardinality of C is the same as the cardinality of the field of rational functions, and then the same as the cardinality of the algebraic closure. So it's just an uncountable field of cardinality the same as cardinality C. Great, but then this means that from this corollary it follows that complex numbers, the field of complex numbers, is isomorphic to the algebraic closure of C of x. And we of course have the obvious embedding of complex numbers into this algebraic closure as scalar rational functions. And this embedding is very, very far from being surjective. We send complex numbers to scalar rational functions. And this means that the field of complex numbers admits many field endomorphisms that are not automorphisms. And the catch here is that all these endomorphisms are not constructible because we need to use the axiom of choice to prove their existence, or the equivalent Zorn's lemma. So the field of complex numbers admits many non-surjective endomorphisms which we cannot construct. Here's an alternative, maybe more direct construction of an algebraic closure. Let K be a field, and let P be the set of all non-constant monic polynomials over K. So the polynomials are Fi, where I goes through some indexing set capital I. Let us consider the polynomial ring Q, and this is a ring of all polynomials with coefficients in K, with variables Qi, where I belongs to the same indexing set. So this is a polynomial ring in a huge amount of variables. This is a really big ring. Let J be the ideal of Q, which is generated by the evaluation of Fi at Qi for each I. An interesting observation is that this ideal is proper, so it doesn't contain the element 1 of J. If we can prove that, then, by Zorn's lemma, the ideal J is contained in some maximal ideal J prime of Q. And then we will see that the quotient of Q by J prime is an algebraic closure of K. So let's prove all the steps. Let's start with the lemma. So we want to show that we can write 1 in the form sum I from 1 to n gi times fi of qi for some gi in Q. So we cannot write 1 as a finite linear combination of the evaluations of fi at qi with coefficients in Q. Let capital F be a finite extension of K in which each fi, where I is between 1 and n, has a root. Let this root be lambda I. Then we have a homomorphism from Q to this F, which is the identity on our smaller field K, and which sends Qj to lambda j for each j between 1 and n, and all other Qj's, those which do not appear in this sum, are sent to 0. And this homomorphism, of course, sends 1 to 1 because it's a field homomorphism, and it sends our sum to 0 because all fi evaluated at qi are sent to 0. Therefore, the equality that 1 is equal to our linear combination is not possible because the left and right hand side have different images with respect to our homomorphism. So this proves our lemma. Now, in order to prove our proposition, we would need the following fact, which is called primitive element theorem. Theorem: let K inside F be a non-trivial finite separable extension. Then there is an element A in F which is usually called a primitive element, such that f is obtained from K by adjoining this element A. Proof. If our field K is finite, we can take as A any generator of the finite cyclic group, which is the multiplicative group of F. Right? So if K is finite, F is also finite, its multiplicative group is cyclic, we can take the generator, and if we adjoin the generators, then of course we adjoin everything. So if K is finite, there is nothing to prove. If K is infinite, then we can embed our field F into some finite Galois extension capital K of K, because our field F is separable over K by assumption. By the Galois correspondence, there are only finitely many intermediate subfields between little k and capital K, which means that there are only finitely many intermediate subfields between little k and F. And since our field K is infinite, and capital F has dimension at least 2 over K, we cannot write this finite dimensional vector space capital F over K as a finite union of proper subspaces. And therefore, there is an element A in capital F which doesn't belong to any proper subfield of F. And this proves primitive element theorem. Now we will use it to prove our proposition that Q divided by J prime is the algebraic closure of little k. To start with, let's discuss that the field extension from little k to Q divided by J prime is algebraic. So each element Qi in Q divided by J prime is a root of Fi, and so it is algebraic over K, because Fi is a polynomial over K. And all these elements Qi, they generate Q, and so they generate the quotient as a ring, and this means that the extension is algebraic. So our extension from K to Q divided by J prime is an algebraic extension, and so we only need to check that Q divided by J prime is algebraically closed. By construction, every non-constant polynomial over K has a root in Q divided by J prime. That's really the construction. This polynomial is listed, so monic polynomial is listed, and so it has a root, the corresponding Qi. So it suffices to show that every polynomial over K splits over Q divided by J prime into a product of linear factors. That's what we need to show. So let f of x be a polynomial with coefficients in K, and let capital K be the splitting field of this f of x. Let us now assume that our field little k is perfect, which means every polynomial is separable. So we prove now the proposition only for perfect fields. So since we assume that our field is perfect, then by the primitive element theorem, which we can use because it uses separability, we have that our field capital K is obtained from little k by adjoining one element A. Consider the minimal polynomial of A, so that's some irreducible polynomial over K, and then that minimal polynomial has a root in our extension Q divided by J primed. And since we have a root, this root gives rise to a field homomorphism from capital K to Q divided by J prime. So capital K is a subfield of Q divided by J prime, but capital K contains all roots of f of x, and this means that f of x splits over Q divided by J prime. And this proves our proposition for perfect fields. And here's an idea how one can extend this proof to the arbitrary case. That's some technical work which we will not do. To start with, in characteristic 0, all fields are perfect, so characteristic 0 case is done. And in positive characteristic, in characteristic P, a field K is perfect if and only if its pth power is equal to K. So therefore, if our field is not perfect, we need to replace it by a larger subfield of Q divided by J prime, which we define in the following way. So we consider the subfield K prime of Q divided by J prime, which consists of all element A, such that A raised to the power p to the power k for some k belongs to our field small k. It is easy to show that k prime is a subfield and that it is perfect. And using Frobenius automorphism, one can show that every non-scalar polynomial over k prime has a root in q divided by j primed. So it's exactly the same condition as we used for k when we defined this field. And then, of course, our proof for perfect fields applies, and this shows that q divided by j prime is algebraically closed. And it's a good exercise to fill in all the details of this proof. Some additional problems and questions. Problem question 1. Prove with all details that K is algebraically closed if and only if all irreducible elements in K of X have degree 1. Problem question 2. Prove that Q overlined has infinitely many non-trivial automorphisms. Problem question 3. Is X squared an algebraically independent over K element of the field of rational functions over K in the indeterminate X? Problem question 4. Prove Steinitz exchange lemma for finite-dimensional vector spaces. So it is formulated in the following way. If V is a finite-dimensional vector space over some field, and X and Y are two subsets of V, then the fact that X belongs to the linear span of Y implies that the cardinality of X is less than or equal to the cardinality of Y. And problem question 5. Give an example of two countable non-isomorphic algebraically closed fields of characteristic 0. Thank you very much and see you next time.